All right, so we'll start. This presentation is about let's start that again. It's about performance in general and on mobile in specific. All right, first a little bit about me, a little bit of my background. I've been a graphics programmer for a long time. I worked on a lot of games for all kinds of platforms. Just a little fun fact, see the Mercenaries game there, the guy in the middle? He's a Swedish guy who's modeled after me, so I'm in a game. Can play me. All right, so the overview of the contents is first a background about mobile hardware. A lot of these things you have heard snippets of over the day, so I'm going to refer back, see if you remember. Then CPU performance, GPU performance, and a little bit about memory usage. So the mobile hardware, it used to be no app store even, you know, and just text-based and then graphics. But today, they're actually fully featured. It's pretty much the same feature set as you have in a high-end desktop, except mobile is slower. They run on battery. They don't have a fan. They're small, and they're much cheaper than a high-end desktop. Therefore, in UE4, we have two kinds of renderers. You've heard that earlier today, referred to the deferred renderer that we use for desktop and the forward renderer that we use for mobile. So even if we have we're saying it's slower on mobile, today's mobile devices are as fast as the previous gen consoles were, like the Xbox 360 and the PlayStation 3. We're talking about 300 gigaflops. But remember, those consoles, they were running at around 720p resolution on a big TV. Today's mobile phones have much, much higher resolution, kind of ridiculously high resolution. Right, but keep that in mind, the 720p. So earlier this morning, you saw this slide, kind of. For 2015, some new numbers is for the Snapdragon 810 and the NVIDIA X1 as new high-end chipsets that are out now. The 810 is, I think the new Nexus device is actually shipped now, so yeah, it's one of in the high-end, it's an 810. By the way, on the NVIDIA side, just another fun thing, you have the K1 from last year. NVIDIA's desktop GPUs, the GPU families are named like Kepler, like K1, and Maxwell, like X1. All right. Other things that I've developed in the mobile world is Metal, the Metal API. We talked a little bit about that earlier, that we've supported it in UE4. It came in iOS 8 and is now out for Mac as well. Back in the days of iOS 8, we made a little demo to show at the Apple conference. And while working on that demo, I did some measurements to see how much faster Metal actually is compared to OpenGL ES. And on the render thread, I noticed that Metal was about 20 times as fast. It means a lot more draw costs you can do, or it means that you leave a lot of CPU over for other things, like AI. So the demo we did for Metal, Zen Garden, has anyone seen that? Who has not seen it? Okay, so some have not seen it. So therefore, I will show it. And maybe someone on Twitch hasn't seen it either, because you should see it. This is the Zen Garden running on an iOS mobile device. notice all the petals, the leaves, a bunch of fish in the water there. But, I mentioned that the CPU is freed up to do other things like AI. That goes for the AI for the fish, for example. This is downloadable on the iOS App Store, so you can check it out if you have an iPhone. So during the first area of this demo, it was a little bit interactive, so you can move across, swipe across the screen to touch the branches. Leaves will magically appear and fall down, and you can swipe on the ground to blow wind through the leaves and they swirl around. You can attract the fish. It's like a, I mean, it's a flocking AI. And then in this section, you can interact with the sand in a draw Zen-like patterns. And luckily, when we recorded this video, he didn't draw something else. You can draw anything you want. And to show the added efficiency on the CPU, on the render thread, we wanted to make a lot of draw calls, right? So all of these butterflies are individual draw calls. So refer back to the, by the way, excellent presentation by CCP earlier. You know, they had extreme performance limitations where they, first of all, they didn't have metal on the Gear VR, but where they limited to 50 draw calls per eye. In Zen Garden in iOS 8, this demo can do about 3,000 draw calls per frame at 30 frames per second. The number of draw calls, you know, goes up and down a little bit, you know, from 2,000 to 3,000, but it's a lot. So that's the kind of efficiency and how technology has moved forward on the mobile world. Thousands of draw calls, no longer limited to 100 or 200. At least with metal, it helps a lot. Then there's another API on the horizon. Vulkan, I would refer to the bottom point there, that Vulkan isn't done yet. It's not public. It's coming soon. It's been developed by Kronos, who came up with OpenGL ES. Now, OpenGL has been with us for many, many years. It's been slowly evolving over the time. Vulkan was taken and developed in pretty much like 12 months. So surprisingly quick committee-based decisions with everyone from the industry participating, from the hardware vendors to software vendors to game developers. But you know, it's not done yet, so we'll see if it's any good. It has the same goals as all these other new modern APIs like Metal and Mantle from AMD, DirectX 12 from Microsoft. They all have the same goal, kind of, being able to do a lot of draw calls, remove driver overhead, and kind of nice for mobile is it raises the minimum feature set to a modern GPU. We'll say more about Vulkan when it's done. All right, so in Paul Oliver's introduction, you heard about tile-based GPUs. On mobile, there's two kinds of GPUs. I'll say there are two, but there's really only one that has any market. It's the tile-based GPUs. The reason for the tile-based GPUs is to save heat and battery power, because it stays on chip. It doesn't go all over the system. The non-tile-based GPUs, which I would call direct renderers, are like NVIDIA, Intel, Vivante. None of them have a really big market share on mobile, but they exist. The one-off is the Qualcomm. Qualcomm is a hybrid. It can do either tile-based or direct. The method chosen is done by the driver automatically, and it can change many times per frame. There's no cost in switching between the two methods. The driver will kind of guess for each render target switch. It will guess, is this render target going to be do with tile base or direct? You saw this slide also a little bit earlier. The tiles. There's the two kinds of tile base. There's the small tiles and there's the large tiles. Small tiles are like GPUs from Image Tech or Imagination Technologies and ARM. The large tile is Qualcomm. So the small tiles, they can do many tiles in parallel on different GPU cores, whereas the big tile, just one tile at a time, and the full GPU does everything. So the benefits of doing tile-based, as I mentioned, it fits on the GPU. It doesn't go to memory. Memory bus costs heat and power. The chip is extremely fast. It's hundreds of, I don't know exactly what, but it's a lot faster than going to RAM. The thing with the tiles is that when the GPU, it gets all the draw calls for a whole frame, it processes all the draw calls for just one tile. When it's done, have the final color, it's done with the last draw call in your scene, and then it outputs that, basically copies it to RAM. And it does all the draw calls again for the next tile. And then the draw calls again for the third tile, and so on. So that might feel like, why does it do all the work over and over again? Well, it doesn't actually do everything over again. The vertex processing is only done once. So the transformed triangles and the vertices are saved to RAM. The green little cylinder there on the right, top right. And then what's repeated for each tile is just the pixel processing. This is an example of how it works on an Imagination Technologies GPU. And if you don't recognize the word Imagination Technologies, maybe you recognize the word iPhone. They may not have anything to do with each other. I'm just saying two words there. I've circled in red here one little portion, which is kind of the secret sauce for Imagination Technologies GPUs. It's a good thing. It's free for us game developers. I'll talk about it a little bit later. What's important to see here is it repeats that dashed box there for the pixels in one tile, and for all the pixels and all the draw calls in that tile only. The unit here, the shader unit, it knows if it has a triangle that crosses many tiles, it will only do the pixels for that tile, so it doesn't do any, actually it doesn't do any unnecessary work. All right, so when I said I would talk about the hidden surface removal a little bit later, I mean now. So this is only on the image tech GPUs. What it does is you don't have to sort, we talked about depth or Z rejection, depth testing, where you wanted to draw the skybox last, for example, so you got occluded. On image tech, you don't actually have to sort. The GPU will do that automatically for you, for free. It doesn't cost anything. It's extra hardware. It doesn't steal any clock cycles from your shader units or your CPU or anything. But it only does this for opaque objects. So it means that, for example, the skybox should be opaque, first of all. Don't make alpha-blended skyboxes by sloppiness. Right? Skyboxes needs to be opaque. It should be drawn at the end of the opaque phase before translucency. In UE4, we try to do all these things automatically for you, but just so you're aware. All right, so let's go a little bit to the CPU. The CPU is basically two things. It's gameplay logic and it's draw calls. The gameplay logic in UE4 runs on a single thread. So if you want to run at 60 frames per second, that means that the game thread has to be below 16 milliseconds each frame. Actually, I'll refer back a little bit to the whole title of this talk was 0 to 60 frames per second. The 0 is if you would try to do the deferred render on a tile-based GPU. So when we're saying that the deferred render is for high-end GPUs, what we're really saying is that it's for direct renderers. It's because of the tile-based nature of most mobile GPUs. They want to do all the draw calls in one batch, like in a batching process. The deferred render doesn't care about batching. It switches render targets whenever it wants to, reads from the previous render target, composites into a third one. That's very bad for tile-based GPUs. So on a tile-based GPU, if you try the deferred render, you can. It's the same feature set. It's high, it's basically the DX12 feature set on all GPUs. That will be your 0 frames per second experience. If you try it on a, for example, an NVIDIA mobile GPU, that's your 60 frames per second experience. But for tile-based GPUs, I'll take you from 0 all the way up. That starts with a gameplay. For scaling and optimization purposes, it's very, very difficult to optimize CPU code. If you just take a quick thing from GPU land, if you want to optimize the GPU, you can just cut some post-process effect, and suddenly you run faster, and the game will still work. But you just can't just cut something from the gameplay, right? Because then you lose the game. The whole game is about the gameplay. So it's very difficult. So I would highly recommend design your gameplay so it will work on your min-spec device at 16 milliseconds per frame without optimizations. We're about make sure that you are GPU bottlenecked, not CPU bottlenecked, especially on the game thread. The way to check that the game thread is fine, even if the game is running at 2 frames per second, your game thread may still be fine. You need to know what to optimize. And the way to do that, the very first thing you do is use stat unit. It will tell you which unit, basically which hardware unit. I don't know why I came up with the word unit there, but I was maybe thinking about hardware units, CPU cores, GPU cores. It can show GPU time and CPU time. It will show the game thread time, the render thread time, and in some cases when we can measure it, the GPU time. The other thing you can do, that's just a quick thing to see if you have a problem at all on the game thread. So don't worry about frame rate at this time. First you need to check, maybe the CPU is fine, you don't need to worry about it. If you have to worry about it, and you're not willing to cut gameplay features to optimize, then you need to profile. We have a lot of stat system in UE4 that you heard CCP referred to. You remember the charts where they had game thread in a graph and a render thread in a graph and so on, lined up with game events. You can use that. You can also use specific CPU profilers like the Xcode instruments, the timing profiler. So CCP mentioned blueprints. Zach mentioned he used the blueprint of the frame tick in his Labyrinth game. But blueprints in general, for performance purposes, is great for prototyping. It's great for fast iteration on an idea. But it's really aimed for event-based logic in a game. So not really doing something every frame or all the time continuously for when something specific happens. Like an enemy gets killed. That's an event, and you can hook up a blueprint to do some gameplay logic based on that. Or a door opens, or events, not tick. But as in all performance-related issues, the one thing you have to remember is measure first, do the optimization, and measure again. Because optimizations is kind of like magic or a box of chocolate. You don't know what you're going to get. The optimization you do may actually make the game slower, or it may not make a difference at all. So if you do any optimization, for example, you make a material much simpler, maybe you're okay with the visual degradation, but make sure it's actually worth it, because it actually may not have saved you any time. So if you're okay, you're running at 60 frames per second anyway, then you don't need to do anything with the blueprints. It's fine. If you check stat unit, your game thread is below 16 milliseconds, you're fine. You don't need to do anything. But if you are running at like 100 milliseconds, okay, time to go and do some optimizations. Perhaps convert some tick blueprints to C++. But as always, I have to profile before and after, so you know that what you're doing is actually has any effect. The other thing that came up was about the temperature on the device. Mobile device changes clock frequency all the time, every millisecond. So many, many times per frame, up and down. So this is a tool. There was a question about if CCP had measured the thermal, for example. This is a tool from Qualcomm called Treppen. I don't remember if it shows the temperature, but it can show you the clock frequencies on each CPU core and on the GPU going up and down. So you can correlate that to your gameplay or events in the game, for example. One thing to note is that the temperature on a mobile device isn't just one temperature. They usually have lots of sensors, from like the processor core to the outer shell of the device. All have different limits that the hardware vendor had decided. When any of these temperatures get too hot, they will destroy your performance. So therefore, when you think about performance or measuring time, you need to measure when the device is cool, and need to measure again when the device is hot. And you could, for example, if you want to go faster between these two states to measure something, you may have two devices, one that is cool and one that has been heating for a while, and then you swap them to test. And if you have a device that is hot, you need to cool it down quickly because you want to do some more testing, put it in a fridge or a fan or something, cool it down. One more thing about the heat. So really, I don't care too much about battery life, actually. I care about the thermal, though. For those minutes that the gamer is playing my game, I want that to be a good experience. When they close the game, if the battery is out by then and he can't check his email, it's his problem, plug it in. Carry an extra battery. That's what I do. But anyway, things that causes heat. CPUs tend to cause more heat than GPUs, which is, I would rather the GPU would be bigger than the CPU in a mobile, but CPUs tend to heat up the device more. So even if you are good on the CPU, like your game thread is well below 16 milliseconds, maybe for some reason you're doing something unnecessary that heats up the device and just makes the GPU slower. So that can happen. Also, the memory, just doing mem copies, the memory bus itself can heat up the device as well. So basically, you need to be efficient on everything on a mobile device because it will hurt the rest of the system. All right, so let's go to GPU performance. So remember that early slide when I talked about 720p? That's kind of the performance of mobile devices today is comparable to Xbox 360 at 720p. But the mobile devices today are much higher resolution. On a tiny, tiny screen, much smaller than the TV that was just 720p. And that was good games we had back then at 360. P3. But basically, my point on that is that 1080p and 4K screens on a small screen like a mobile device, that's just a marketing bullet point. It's not really that useful for gaming purposes. For a game, I mean, it's useful for UI, possibly, but not necessarily for 3D content. What is more important than resolution is anti-aliasing. When the first iPad Retina display came out, I tried it, and I tried native resolution, and it was, oh, it's okay. And then I went back to lower resolution and tried MSAA, and wow, it was beautiful. It turns out, or just by coincidence, MSAA is one of those things that tile-based GPUs are much better on than direct renderers. So your cell phone can do anti-aliasing much better than your high-end PC, you could say, at least MSAA. The reason for that is that the tile contains all the screen colors, so that would be multi-samples on the GPU, and when it copies it to RAM, that's when it does the multi-sample, the downsampling for MSAA. It's basically free. Also, the first point there about GPU optimization, the easiest thing you could do is just lower resolution and if things don't run faster, which is some Xbox One games have a little bit lower resolution than PS4 games. It's easy optimization, right? So we talked about some of the UE4 stats you could do. You saw the graphs from the CCP talk. That's kind of like the stat unit graph thing, though by default, those graphs are averaged. So they look pretty and curved instead of going spiky like that. But what they did was use the raw data, it looked like. So you can actually see individual spikes better. There's pros and cons for each method. Use both, whatever you need. The simplest one was the stat unit. It just shows 3 values on the screen all the time. Those are averaged also, by the way. I'm going to talk a little bit about the shader complexity view mode that you saw a little bit earlier in one of the earlier presentations as well. There's a documentation link there. You can look at the slides after and go to that link later. The easiest one was the stat unit, right? In this case, I took a screenshot from doing this on a desktop PC where the API allowed me to measure the GPU performance. In this case, the game thread just says, I just shortened it to game colon, but that's game thread running on one CPU core. It's at 1.5 milliseconds. It's totally fine. The draw, that means the render thread. It was shorter to type draw than render thread. What it is, the render thread, 2.5 milliseconds, that's totally fine. The GPU, in this case, is running at 16 milliseconds. That is the bottleneck, and that's why the overall frame rate is exactly 16 milliseconds. Frame rate is going to be exactly the same number as the slowest one of these. In this case, it's running at 60 frames per second already. Don't need to do anything. Actually, probably V-synced. That's why it's 60 milliseconds anyway. Stat scene rendering, if you want to look at the render thread performance, that's basically all the draw calls, the OpenGL API, the driver overhead will come from this. This is the part that any API like Metal would help. It helps on these times. The different passes we do during scene rendering. In this case, the rendering thread was fine. So we go on to the GPU. You saw something similar like this, with different colors, where green was fine, red was bad, and purple or white was really bad. It's an approximation. It basically just counts the number of instructions in the pixel shader. It may even count D3D instructions, even in the ES2 preview, where I don't remember exactly. Not GLSL instructions, or definitely not the hardware GPU instructions. But it's a good approximation. And I think there was a question whether you could change the coloring scheme. I believe that that is indeed a INI setting, so you can set the colors if you want to have a different range or your performance limitations are a little bit different than default. Again, another thing that is special to mobile GPUs is that FP16 or 16-bit floating point resolution is pretty much twice as fast as full precision, that is 32-bit precision. If you're running your own renderer engine or running shaders, you should really think about this and use FP16 as much as possible. You know, in UE4, we try to do it for you as much as possible. Some things you can think about when you're drawing or creating materials is that things like position, world position, will have to use 32-bit precision because it doesn't fit nicely in 16-bit. Whereas colors, for example, any math you do with colors would be a normal maps, perfectly fine for 16-bit precision. And it's really twice as fast nowadays. So here's the reason why the deferred render doesn't work on mobile. It's this slide. Any questions about that? No? Oh, it's the switching of render targets. Like on a tile-based GPU, you don't want to do a lot of draw calls, wait until all of those draw calls have been processed for each tile, saved out to RAM, and then in the next draw call, you want to read the results. That's going to be slow on a tile-based GPU. That's why this little orange thing says that it doesn't matter for NVIDIA Tegra GPUs. It's because it's a direct renderer. The best performance you can get on a tile-based GPU is you don't switch render target at all, or frame buffer object is the same thing in OpenGL versus DirectX terminology. So you just set it run it to one time, you do all your draw calls, and then you output that to the screen. That's exactly what CCP did in their game. No post-processing, because I would have to read from the previous render target and so on. That's how you really reach 60 frames per second on mobile. However, if you don't have any post-processing, you don't have tone mapping or HDR, it might be difficult or impossible to do lighting, which is why CCP's results are so impressive, because it's not using HDR. In UE4, we decided to go with HDR for a specific reason. Not just because it's 3 cool letters, but it's because it makes the content cross-platform. If you have make textures, it's hard to use texture and lighting in a gamma space non-HDR game and use the same assets in an HDR game. It's kind of difficult because the color ramp is different. So if we just decided that, okay, all UE4 platforms should use HDR, that makes the content cross-platform and the engine cross-platform. So that's why we did that. So the bad thing is that some, and I'll say it's the Mali GPUs, they don't expose FP16 render targets for unfortunate historical reasons. That means that we can't store FP16 HDR colors in the render target on those GPUs. And that makes lighting and all post-processing very difficult. So for those GPUs, we came up with a compromise in UE4. We called a mosaic HDR, where we basically store, instead of storing a 16-bit floating point, we store 2 8-bit values, 2 pixels represent the value of just 1 pixel. So it basically halves your resolution or use twice as much data per pixel, but it's the same thing as FPS 16 anyway. That would also use twice as much memory for a pixel. But even the mosaic, even though we can have HDR with that, it does prevent certain post-process effects still, like bloom, which is something you would like to have in HDR, because you can have very bright colors, so you want to be able to bloom that. So kind of a little bit defeats the purpose. So we made something new today, or yesterday. It was pretty recently. It's not out yet, but I think it'll come out in 4.10 or maybe 4.11. On the left-hand side, you see the current compromise, the mosaic HDR, where we can't have bloom, primarily for ARM Mali GPUs. In the middle, you have how it looks on a device with full FPS 16 render target, full HDR colors, where we can have bloom. And then on the far right side, you see our new encoding, where we store HDR colors in 8-bit with RGB plus an exponent encoding. So that's new, coming. Whoa. It just like optimized all my slides away. Okay. So another optimization. Zach mentioned this and showed you how to do it, the quality switch that you can put in a material. Not just to make something like for decals, how to make decals look prettier if you don't have all the features, but it's good for optimization purposes too. You can make a fast version for low-end devices and instead a high-quality version for high-end devices using that quality switch node. Just plug that in, and then you plug in your two different expressions. One is fast and one is better looking. Problem is that this is per material. We have to go into each material and do these optimizations by hand. So we have new stuff. I think we went a little bit into that in a previous presentation, but this is a global wide sweeping, cross game sweeping settings. You can see it's going to be in, it's not in 4.9, 4.10. It's going to be in 4.10. So it's in the project settings. You can see I clicked on the Android ES2 quality, and then that beautiful UI will show up with checkboxes. It'll override across all the materials in one go to disable the roughness, for example, for material in one go. The low, medium, and high, which someone said, why is it low, high, medium? Well, for some reason in this UI it is actually low, medium, high. But we're still coders, so if you look at the numbers that it actually translates to is low, high, medium. So it still got you. Sorry. We're going to do something for Fridays, right? So yeah, it sets up the quality level versions for all materials in one go, which this is the third bullet point here, is that the device profile is the one who selects which version it'll use, if it's going to be low, high, or medium. So, device profiles. They're awesome, but can be complicated, maybe a little bit tedious to set up, and especially for QA to test all of the different devices and making sure that all the settings are adjusted properly. UE4 will detect the device at startup. It will check GL extension strings, see what features are on. It will try to detect which GPU it is, and based on that, choose a device profile. So once UE4 has chosen a device profile for you in C++, the device profiles themselves are written in INI. And they set things up like they adjust the Mobile content scale factor, for example, is for resolution adjustment. Bloom quality is to make the Bloom process faster or slower, but better looking, or disable it all completely. You have the link there for more documentation on the device profile. And Alan showed this, I think. The device profile editor, you can see all the device profiles, and you can go in there. Instead of going to the INICE directly, you can click on the CVAR's little wrench icon there to go and change. Oh, I think Zach actually showed that too a little bit. So we have something new. So instead of having to modify the C++ code in the engine, if you want to modify how the device profiles are selected at startup, you can now change the selection rules in INI. You know, it's still complicated, but you don't have to type C++, and you don't have to recompile and so on. Also, an INI file is easier to patch. So profiling. Never do an optimization without profiling before and after. Actually, in our status emails, if we do a optimization at Epic and we don't have before and after numbers to prove that it was actually good, it's not good. I have to report numbers. We have the cross-platform tools that is built into UE4. When you want to, or when you need to go deeper, there's hardware-specific tools. CCP, they mentioned that they use the Qualcomm profiler. It is the second one there on the GPU, the Adreno profiler. They may have changed the name on that now, but anyway. They're kind of, I didn't sort them based on market share, but you have the Apple iOS is a common device in market share. So the GL debugger, or the Metal Graphics debugger, maybe it's called nowadays, is one very good tool to use. Qualcomm and ARM are the second ones to use. And then you have NVIDIA on a little bit lower market share, and ImageTech. But ImageTech, they make GPUs for Android devices too. For CPU profiling, if you need to dig deeper rather than just our stat system, which, by the way, you should do like CCP did daily reports. They gather the stats and save up. That's what we do too at Epic when we make games. Our QA personnel, they will run through the game and save up stats reports like that in Excel. They would go and track curves over time and regressions or optimizations on performance. All right, so I'm going to show you, here's a screenshot on the Xcode graphics debugger. I've done one capture of a frame in, this is the Soul dungeon, no, just Soul, that we showed running on Android at a GDC a while. So for some reason, I made a capture on iOS, even though it was an Android demo. But it's a pretty fantastic tool, actually. And since the iOS devices are a tile-based GPU, the results you get from that would be similar to other tile-based GPUs on Android, for example. So it's still a good tool, even if you're just making an Android game. On the left side, you have all the draw calls. And we have ways to annotate the draw calls with, first you can see there we have annotated with the name of the path, but we can also annotate each draw call with the name of the material used in the UE4 editor. So if you have a draw call like in the base pass, just an opaque draw call, usually all the draw calls have completely different characteristics. You have like 90% of all the draw calls take no time at all, and then there's 10 draw calls that are like the real worst offenders. Those are the only ones you need to optimize. You don't need to optimize everything. The frame time itself, the frame rate, doesn't tell you anything on what to optimize. You have to go and look at which are these 10 worst draw calls, those specific ones. And using a tool like this, you'll see exactly which material it is. And you may notice, oh, the material, I forgot to change that. It was just a prototype. It wasn't supposed to be in the game. Right? Actually happens a lot. In this case, I have selected anti-aliasing draw call at the post-process. It actually says post-process AA there. On the right side, you can see the actual shader code for that anti-aliasing method. If you're a programmer, a graphics programmer, that right side is edit and continue. So you can change it. You can comment out some texture lookups, and you will see how much faster or slower that change did to your draw call. The important one is down there in the center. It says fragment shading, shader duration, 1.73 milliseconds. That's for the pixel shader. The vertex shader, takes vertex shading 0 milliseconds because it's just a full screen quad. Takes no time at all. But the pixel shading with all of those texture lookups takes quite a while. Well, it's about 2 milliseconds. If you wanted to reach 16 milliseconds, you have to tell yourself, what's the trade-off? Is it, do I need this? Should I disable it? Or should I do something to optimize it in between? It's your choice. But at least now you know that, what is it, 10% of your frame time or 20% of your frame time is for anti-aliasing. This is the screenshot of the Qualcomm Adreno Profiler tool for Qualcomm devices. Just as a general rule, all mobile phones in the US are Qualcomm. All Android phones are Qualcomm because of LTE in the US, pretty much. In the rest of the world, there's all those other vendors come into play. It is actually a pretty good tool. NVIDIA, they have tools too. It's kind of interesting. Well, it's a little bit older screenshot, but the NVIDIA tool on the right side has, it measures the draw call different ways. I think you can scroll to the right, and there's like 3 different ways that measure all the draw calls. Because GPUs are highly multi-threaded, they, a CPU, when it changes, this is the big difference between CPUs and GPUs. CPUs, multi-threading, it takes forever to switch thread. It takes an interrupt, it goes to the OS runs the scheduler, decides what to do. It takes forever, like an eternity in clock cycles counted. GPU does threading in hardware. It switches thread every instruction, or every second instruction, every 2 clock cycles. And it can have thousands of threads running in parallel. That's why CPUs can never be as good as GPUs, because of multi-threading. And that's why GPUs aren't very good with if statements, for example, or dynamic branching. Has usually been a problem. So that's why the NVIDIA tool measures everything many times, because all of these threads, all the draw calls are actually being executed at the same time, a couple of instructions each, and then it changes back again. So one draw call will affect the performance of another draw call. So it's kind of tricky. You can't just measure the start and the end time of each draw call, because they're actually executed at the same time, all of them. So it's a tricky thing to measure, and NVIDIA tries it one way. Here's a tool for imagination text on Android, and the ARM Mali graphics debugger. Okay, so at the very end of this presentation, talk a little bit about memory usage, because that has to do with optimization too. The one thing I want to highlight is texture space. You should you should always, during development, maybe not the very first day, but soon in the middle of the game development and surely at the end, keep track of your memory usage for textures. Because texture space, it affects both the memory usage, which can cause out-of-memory crashes that you don't want, force close, and it affects the download size and how quickly a gamer can tap your game and start playing. And texture is like the biggest offender, usually. On mobile, there's unfortunately no good standard for what texture format to use. There is only etc1 that has to be supported by everyone. Unfortunately, etc1 sucks. It can only compress RGB. If you have an RGBA texture, it'll have to be uncompressed or separated into two textures. And they look like shit. So what you should do is to utilize the GPU-specific texture format. So on Qualcomm, they have a format called ATI-TC. On ImageCheck or on iPhones, again, just two words, have PVR-TC format. So what you should do, don't be sloppy, don't use ETC, not even ETC2, because it's still not completely supported by everything. Make multiple SKUs. A small, efficient, good-looking SKU for Qualcomm devices with Qualcomm-specific textures, one for Mali, one for ImageTech, and so on. But the future looks brighter, or much bluer in this case. This is a normal map. This comes from our Sun Temple sample in UE4. I've zoomed in on one spot just to show you how important it is to select a good texture format. There's a new format called ASTC. It is an open, free standard that anyone can use, any hardware can use, no patents, no licensing fees. So it's coming into OpenGL. It's supported on most modern mobile phones already. In this case, I've shown a normal map that is uncompressed, which is what you would get if you use an RGBA texture on ETC1, like if you would be sloppy when you make mobile games. 17 megabytes in this case for that texture. And this is an actual texture that was in the Sun Temple map. This is not just made up. It includes the MIP maps, by the way. Then the ETC compressed texture, it's compressed down to 3 megabytes. Then for ACC, I chose a 6x6 block just because it kind of matched the memory footprint of the ETC. You can, however, choose much less memory usage, but you would degrade visual quality a little bit. But even at the same memory footprint, a little bit better still, it looks much better than the ETC compressed one. I mean, it looks almost identical to the uncompressed, but a much smaller footprint. And you really shouldn't make your games look like the middle one. Don't do this, right? Just don't do it. I will hunt you in your dreams. Utilize what the powers have given you, what Qualcomm and ImageTech use their formats, or use ACC. And we support ACC in UE4. Just go down there, package for Android, and choose ACC. And it's also supported on iPhones in metal. All right. Any questions? Performance? All right.
Do we have to do anything special?
You have to ask it again.
Do we have to do anything special to get all the benefits of metal?
No, you just select metal as the iOS target. Yep. So, metal is only supported on iOS 8 and up, and only on those devices that supports it.
You mentioned that the gameplay thread runs on a single thread, right?
Yes.
So if you're writing C++ code, is it dangerous to use some kind of thread pool library like TBB or PPL or an Apple Grand Central dispatch?
No, that's good. Definitely do that, especially now that mobile devices have more and more CPU cores on them. You do need to measure before and after, because if you're using more cores, it can heat up the device more, and then that destroys the GPU. And
sorry, is there a danger with in the threads?
Right.
Say, having some bad
don't
race
use
conditions with Unreal 4. That's why I'm asking.
Right.
Is it,
Don't use a U object on another thread. U objects are game thread only. So you would, when you manipulate that, you would have write out a small separate struct. It's normal multi-threading work, and give that data to the worker thread, and it comes back with the data.
Sorry, just one more quick question.
Yep.
The other question is about GPUs. So you mentioned about the part about the textures, right? So my question is, how expensive are texture lookups? So is it cheaper to say you do some pre-computation, you pack in say a 1D texture, do lookup, or would you rather do the actual computation on the pixel shader and do the math? It's like, what's the trade-off? Like,
Right, that's a very good question, and the answer is different from GPU to GPU a little bit. Generally speaking, the memory is slow, and the GPUs are very, very fast. So generally speaking, you have quite a few instructions that you can do for free for the same cost as waiting for a texture fetch. But it all depends on how much you're using the memory bus anyway for other things. Remember, on the mobile, the CPU and the GPU are on the same chip, one memory bus. So what you're doing on the CPU may affect your GPU texture fetches, and the other way around. If you're doing a lot of texture fetches, you may find your CPU code run slower because of memory fetches there. Some, or many, or even most older mobile devices had a fixed cutoff that the CPU could use this and GPU could use that, but it's becoming more dynamic as we go forward. The real answer is that you have to measure before and after. Try that's why kind of it's so nice to do it on the iOS in the Xcode, because you can just change the code on the right side, comment out a texture fetch, write some ALU code or math instead, and just hit enter basically, and it will remeasure it and see, you can see it right there. But again, since all of the draw calls are done in parallel at the same time, what you're doing in one shader is going to affect the other thread. So it depends on how many texture fetches you happen to do at the same time in all the draw calls. So you have to measure.
So on tile-based GPUs, forward rendering for dynamic lights is slow. Could you suggest some other methods if I had lots of dynamic lights in my scene? Some other rendering methods for that?
Yeah, don't design the game that requires a lot of dynamic lights in your scene. There's a great point in the CCP, so if that's okay to say, about the alpha blended translucency port that was done at low resolution. When you do that, in general, when you composite, you have to do some depth occlusion yourself. Normally, that's what you have to do. And that will take some time. You'll have to do the Z-test yourself to see if the translucent particle should go behind or before an object. But these smart guys from CCP, they just talk to the game designer. Don't put particles when there are stuff that could occlude it. So they only put the particles in the center of the screen where there's nothing that would occlude it. So they didn't have to do that, and it went much faster. So design your game accordingly. We support four dynamic lights now, point lights on the forward rendering path. So just make sure you don't need more than 4 at a time, and measure before and after.
We have time for one more question.
Can I ask you something about VR? Is that all right?
Sure.
I heard something about like free frame rate. Is that something you guys are working on? It's like a term that I heard from a podcast.
Is that a variable frame rate?
It's something about like draw calls. That VR's like rendering graphics.
Oh.
Yeah.
Well, actually, I thought about when we talked about VR, there was a question about if you can take advantage of the fact that the two eyes are close together. There's new technology in the works, extensions, OpenGL extensions, some D3D hacks, where you do all the draw calls for both eyes one time on the CPU, and the GPU executes it twice, one time for each eye. Is that the kind of thing that you're looking for? Like what in APIs, rendering APIs, and if UE4 takes advantage? Yeah, so we did a demo. We did a demo where we wanted to take advantage. We did take advantage of that for NVIDIA, like the Smaug, the Hobbit VR experience. Used that trick. Where we also wanted to use, well, kind of. We wanted to use different GPUs, different actual desktop graphic cards for each eye, but it went so-so. But yeah, so there's various hardware, but there's nothing. Nothing really has come together for VR, but it is on the way. And you can continue to ask me questions after this session, like outside here. Ask me anything except my social security number.
Thank you, Smetas.
All right.